I'm gonna have a test on Friday.
Yeah, Friday, right. We have the first midterm, right? On Friday. What do you guys want to do on Friday? What do you want to do on Friday?
Postpone the test on Monday.
Will it help if you move it to Monday?
Yes.
Yeah.
You will agree to move it to Monday? Any objections?
I have a question. Are we gonna get, like, can we find out how we're doing in the class before drop day?
No one drops my classes. You either get an A or fail. They want to move the test to Friday, to Monday. Will you go with that?
Next Monday?
I suppose. They didn't say which Monday. You don't have any problem. Okay, we'll move it to Monday. That means you have more material to be tested on. And I'll have more time to think about harder problems. Okay. We'll move the test to Monday. I don't know if other people that are not here at this point here will have any issues or not. But if there are any issues, you take care of them. Okay. Yeah, the reason I had it on Friday is the drop date. I remember that. But that happens usually with lower level classes. Senior and graduate level classes, you guys know what you're doing. You came here with your own will, right? And decide your name in the course. So. No dropping. So we're supposed to talk about scattering parameters, right? I know I did not finish that diagram to the full extent that I usually do for the waveguide, but that was just like an appetizer, right? We'll get to the main course later. We did the same thing with the scattering parameters. We had also a taste of it at the beginning, and the reason for that was the laboratory. People in the lab needed to know a little bit about the S parameters before going to the lab. Like we said that lecture, the scattering parameters is the favorite tool to use to analyze high frequency networks. The reason for that is it talks about power transmission and reflection. It talks about power flow. How does power flow? It talks about standing waves. It talks about all these things. While impedance, can be used to some extent, but you have to be well trained in impedance to see through, and it's not that easy. Right? Admittance is the same way. We said impedance is preferred to use to describe networks that are in series. Right? For example, if you have a two-port network, another two-port network, the impedance parameters here, impedance parameter there, if they are connected in series, and what does that mean? That means the current flows here, that comes back out here is the same current that flows in here, comes out there. Because that's what series means, right? Series means the same current flow. So unless your network are connected that way, the impedance analysis would be kind of difficult, right? If that's the case, you can say the impedance matrix here plus impedance matrix, they give you the total impedance matrix, for example. Obviously, the series has to be also on the outside, so the same thing has to happen that way. So these two networks are in series, and we seldom connect things in series in the high frequency networks. We like more the parallel, and the reason for that is we need to have a common ground. here, if you connect this to a ground, this whole network here is floating, right? And the ground is only local to this network. To talk about networks in parallel, which solves the ground issue, then this would be the same as that, and you can connect them to ground. Okay? In this case here, you can talk about adding admittances. And we use that in the middle high frequencies, like the megahertz. We usually use the Y parameters with no issues whatsoever. When you go to microwaves, neither one represent the analysis convenience, or gives us analysis convenience that we need, especially if you're dealing with a waveguide. What are your nodes? What are your wires? Right? What is your voltage? When you talk about waveguides, you won't see any of that. So instead of working with all this, we decided to work with what we call the scattering parameters. And the scattering parameters are related to the signal flow in your network. So what we do is we look at a network like this and say, yes, true, there is voltage and current, but at the same time, we can argue that there is a signal that goes in and a signal that comes out. Especially in the light of the matching discussion that we had in transmission lines. If you have a mismatch, it means there is a reflection. Right? And we decided to label the signal in as A and the signal out as B. And as many ports as you have, you can just put subscripts. So that's A1, B1 for port 1, and for port 2, you still label A2 and B2. And it doesn't matter which one of these arrows is on top and which one you draw on the bottom. Okay? The order of drawing these arrows does not matter. Voltage and current, the polarity is important, and you have to watch for that. You know, if you say this is plus and this is minus, all right, that's the notation or the convention that you use. But the A and B can be drawn. See, I drew it on the opposite side, on the output side, and that's also typical because the way we draw the signal flow graph, we think about signal lines going this way and signal lines coming the other way. And obviously there will be signal lines also branching off from the input side coming back, and signal branching off from the output side also coming back. So that's your A1 here, that's your B1, that's your B2, and that's your A2. Each one of these lines represent a coefficient or a multiplier, if you wish, for the signal to go through, and we'll call this one here S21, this one here is S11, and this one here is S22, and this one here is S12. So we can write the matrix B1, A1 in terms of I guess we wrote it the B1, B2 in terms of A1 and A2. I'm thinking about the transmission matrix for some reason. I went off track here. Okay. The B matrix in terms of the A matrix. When we write the B, A mix, that's really a convenience that we do for the transmission matrix. We'll get to that later on. S11, S12, S21, S22. And that's what we call the S matrix. The S parameter matrix. So you can write your B1 as two components. Component coming from A1, this component here, and component coming from A2, this component there. So the B1 is the sum of two elements. So here it is, B1 is S11 A1 plus S12 A2, the two elements. This element here is what I'm showing in yellow, and this element here is what I'm showing in blue. Likewise, you can write the B2 as S21 A1 plus S22 A2. That kind of representation is nice and simple, obviously, for a 2 by 2 matrix. However, if you have a multi-port situation, suppose you have a network, whatever the shape of the network is, and you have several ports. So there's port 1. I'm using blue for the A's. Okay, that's A1. Port 2 will have an A2. Port 3 will have an A3. And port N will have an AN. And there are several of those. And then you have a B1, a B2, a B3. And like I said, it doesn't matter which side of the story that you write things on. So you can write your B1, B2, Bn in terms of A1, A2, An. And that will be the diagonal elements. Okay, that's how your matrix looks like. Now, we can write each one of those as an equation like this, all right? So if you'd like, you can write B sub I is equal to summation on the J of S I J AJ, right? And that goes from 1 to N, if you wish. You can write that. Now, how does this relate to voltages and currents? Okay, and that gives us a tool to use in transmission lines. The transmission lines we're dealing with voltages and currents, and also we can work out with impedances. What if I have a network of a transmission line and an impedance or a shunt admittance, what have you? How can you get the S parameters for that? So based on that, we do a simple analysis here. I'm going to redraw this diagram a little bit bigger so I can show the voltages and currents as well as the S parameters. Here's a two-port network. What's inside here could be a transmission line, Z's, etc. Whatever is inside here. Okay? And I'm going to do it in 2 ports, or even a single port for now. Okay, I'm just focused on 1 port here. You have a plus minus V and a current I. I'm working in phasors here, okay? V1 and I1. Let's say this is port 1. I can repeat all that for all the other ports of the network. Here you have an A1 and a B1. Well, we know very well that we have voltage waves that goes into that network as a result of this. Right? This came obviously from a source here that eventually is pushing a V plus, and there's a V minus, right? These are the two waves that we have that correspond to the signal flows that we have. And the voltage V1 at this point is simply V plus V minus. Right? If you go to a transmission line, the voltage here V of 0 is V plus e to the minus gamma z, which is 0, plus V minus e to the plus gamma z, which is 0 again. Z is 0 at the beginning here. I'm at the input side, so basically that's a 1 and that's a 1, so it's V plus equals V minus. Okay? That's really your voltage at the input side. It's not equal to the V of the source, of the generator, right? That's not. I1, again, if I do the same thing for a transmission line network, that's going to be V plus minus V minus over Z naught of the transmission line. Correct? So I can borrow these because, you know, I can think of a transmission line here that's a very finite short length. I can use that kind of concept. So the V plus sounds like a good candidate for the A1. And the V minus is also another good candidate for the B1. Right? These are very well matched to our need, except for one thing, that we decided that the A's and B's are going to be normalized. Right? They're not a voltage or a current. They are actually normalized square root of power. Right? I don't want to make the A and B labeled as voltage or current. I want to make it such that. So here's, it's a choice we make. All right? I'm going to write it as a choice here. That the A magnitude squared represents the power flow in the positive direction, and the B magnitude squared represents the power flow in the opposite direction. You can work the A's and B's anything you want. And you can define your own S parameters if you wish. But that's the one the convention agreed to. Everyone agreed that it would be nice to work your A and B such that if you take A magnitude squared, you get your power flow in this direction. So the total power, if you wish, that flows into the network, P total, will be simply P plus minus P minus, which is simply A magnitude squared minus B magnitude squared. That's a great convenience that results from that choice. So I need to choose the A and B such that they meet that condition. So let's see how much power we have. So how do we get the power? To get the power, in this case, you simply multiply the V1 by the I1, right? That's your total power. This network here is getting power here. P total in this network is equal to V1 times I1. And if these are peak, then you multiply by half. Right? I need some space here because I'm forgetting something important here. Real part power. Okay? The complex power obviously is you multiply the two by each other, but to get the real power, you need to do that. So let's multiply these by each other. So we have the real part of V plus V minus times the conjugate of V plus, so it's V plus conjugate minus V minus conjugate over Z naught, if you wish, conjugate. multiply these. I'm going to take this out as my R naught, which is typical situation in my impedance. My impedance here is a reference impedance, really. Because if I have transmission line or not, I can, like I said, claim that I have a very short transmission line here, okay? And take the limit that that length is 0 and the transmission line is gone. Okay? And I can choose that transmission line anything I want. So I can define my S parameters any impedance level I want. So I'm going to say 1 over R naught, real part R, and instead of calling it R naught, actually that's not an impedance. It doesn't have to be any of the impedance. I'm just going to call it the reference impedance. And that's true. Once you define your S parameters, people are going to ask you, what's your reference impedance? Because you can choose anything you want, even though that your transmission lines are 100 ohms and you chose 75 as your reference impedance. It doesn't matter. Right? If you have a good reason to do that, you do it. So the S parameters are not unique to the network if you don't define the reference impedance. Obviously. You can choose any reference impedance and that changes your S parameters. So that's now a reference impedance rather than a characteristic impedance here. Okay? Because like I said, that network may not have a transmission line to start with. So the real part of this, and you work this one out, and you end up with V plus magnitude squared, and you end up minus V minus magnitude squared. And someone will ask, what about the product here and the product there? These two terms here add up to an imaginary quantity, and the real part is here. And you can prove that. It doesn't take much effort. The cross products between this and that, and this and that, you can see if this one here gives you a real part, it's equal to that real part, and the minus sign will cancel the real part. You end up with imaginary minus the conjugate of the other imaginary, that means twice the imaginary, real part of the imaginary is 0. Look at this. So how about if I get the R naught inside here, and the R naught inside there? And I want to compare this equation now with this equation. I guess I already have my A and B worked out. That means that choice that I made and using a reference impedance, that means I'm saying that A is simply equal to V plus magnitude squared over R naught, and the V magnitude squared is equal to V minus magnitude squared over R naught. I can go back here and get the V plus from this expression. Multiply the Z naught here and add, you end up with 2V plus. And this one is simply equal to that. Wait a minute. Magnitude is only on the numerator, not on the denominator. I'm missing a square root of 2, square root of 1. This becomes a square root, I'm sorry. This is A magnitude squared. That means that, oh, that's still squared. Okay, so there we go. I'm copying things wrong. Let me rewrite this part. Let me rewrite. So this is V1 plus Z naught I1 magnitude squared over 2. Magnitude squared divided 1 over R. And this here, 1 over R naught, again magnitude squared here, V1 minus Z naught I1 over 2. Right? V1 plus Z naught I1 over 2 gives you that. So the A is 1 over square root of R naught of V1 plus Z naught I1 over 2. And the B is equal to 1 over square root of R naught V1 minus Z naught I1 over 2. Okay. So if you have a network with voltages and currents, you can get your A's and B's that will meet and make this choice real. Okay? That's if you want to get the absolute A and B. If you are interested in the S parameter, it's a ratio, right? So if you are doing B over A as a ratio, whether it's B11, whatever, BI over AJ, obviously that will cancel out. So eventually what will be left is V1 minus Z naught I1 divided by V naught plus Z naught I1. Okay? So if you are simply getting a ratio, these quantities here will cancel with each other. Okay? But if you want to get the A's and B's for the power purpose, then obviously you need to worry about the 2 square root of R naught being in the denominator. The familiar form for this, that if you open in a book, you will see 2 square root of R naught here. Okay, that's how it usually is represented. Voltage minus Z current, voltage plus Z current. Okay, that's how you typically see it written in that case. All right, let's take a small example here of a network. I want to get the S parameters of that. And my network is simply an impedance. All right, that's all I have. Find S parameter. One way is to simply do a V and I. Okay? That's how we label it. The voltage plus is on the upper node, and the current goes in to the network. All right? So, can we write the A1 and B1 and A2 and B2? A1, B1, A2, B2. The A1 is V1 plus Z reference, Z naught, all right, times I1 divided by 2 square root of R naught. Well, it's the same reference, so it's real. I chose my reference to be real. V1 minus Z naught of R naught I1 divided by 2 square root of R naught. V2 plus R naught I2, 2 square root of R naught. V2 minus R naught I2 by 2 square root of R naught. Okay? Obviously, to get the A's and B's in terms of each other, I need to get the V's and I's in terms of each other. V1 is equal to, first of all, I1 is equal to minus I2. Right? Second equation I have is V1 is equal to I1, I'm sorry, is equal to I1Z plus V2. I have 6 equations, right? And how many unknowns? 4 V's, I'm sorry, 2 V's, 2 I's, that's 4. And 4 A's and B's. So 8 variables, if you wish, or unknowns. And I have 6 equations. I can use the 6 equations here to reduce the 8 variables to 2 equations. And the 2 equations that I want are V1, V2 is equal to S11, S12, S21, S22, A1, A2. If you have a clear mind and sit down with this, it will take you about 15 minutes or so. Very clever, maybe it take you 10 minutes to reduce those 8 equations. I'm sorry, the 8 equations we have on the board, the 6 equations we have on the board, and the 8 variables to 2 equations that way. It's not hard. It's just I'm sure that you'll do some, unnecessary steps in between. So that's one approach. Well, if I use my bounce diagram, the one I learned in class a few lectures ago, I can get things much easier. I'll combine the bounce diagram with a basic concept, which we also talked about in the earlier lecture. We said to get S11, all what you need to do is divide B1 over A1 when A2 is 0. A2 is 0, it means you have no signal coming from here, and that means port 2 should be matched, right? No source in port 2, and also it has to be matched. Matched to what? Matched to the reference impedance. We don't have a transmission line, but we have a reference impedance that we agreed is going to be the reference in all this analysis, which is R0. So what I do is I hook up R0 here. That takes care of this one. Now I want to do B1 over A1. Simply divide these by each other. Right? So if I divide B1 by A1, I can get V1 minus R0 I1 divided by V1 plus R0 I1. How much is V0? I'm sorry, how much is V1 and I1, okay? Well, we'll fix V1 to be an unknown. Everything else can be determined as a result. I1 will be what? V1 divided by Z plus R naught. So that's equal to minus R naught V1 minus R naught times I1, which is V1, 1 over R naught plus Z. And here, it will be V1 plus R naught, V1, 1 over R naught plus Z. V1 cancels out. And I get what? R1 plus Z minus R naught divided by R naught plus Z plus R naught. So I end up with Z over 2R naught plus Z. That's your S11. We're still using the same equation that we wrote before, right? But however, like I said, we can use the bounce diagram concept. So that was method number 1. There are so many methods, okay? That's method number 2. I'll show method number 3. S11 is equal to B1 over A1 when A2 is 0. That means reflection coefficient gamma at the input when A2 is equal to 0.